Hello and welcome back to AP Psychology. I'm Miss Lee and we are still in Section 3, Sensation and Perception. This is Section 4, Hearing. Our learning target today is to describe the hearing process, including the specific nature of energy transduction, relevant anatomical structures, and specialized pathways in the brain for each of the senses. If you haven't done so already, go ahead and grab your notes and let's get started. In a very similar way to seeing, we hear wavelengths of sound. So just a couple of concepts that you need to know. The frequency of the wavelengths is the pitch. It's the dimension of frequency determined by wavelength of sound. This is measured in hertz. Humans can hear sounds at frequencies from about 20 hertz to about 20,000 hertz. Hearing is best around 3,000 to 4,000 hertz where human speech is centered. So the higher the frequency means the higher the pitch of the sound. Intensity or loudness, this is the amount of energy in a wave determined by amplitude related to perceived loudness. Think back to our last video when we were talking about amplitude. That's the height of the wavelength. Loudness is measured in decibels. You will have directions on how to watch this video in class, but I encourage you to do so as soon as you find out. Okay, here is the anatomy of the ear. So we'll start just like we did with the eye. We'll start from the left. So here is the outer ear, the outside part of the ear that you can see that is accessible to you. This outside part is called the pinna. And then as you start traveling into the ear, that is the auditory canal or the ear canal. Then you get to the eardrum. This is also called the tympanic membrane. And this is kind of the entryway into the middle ear. There you see the three smallest bones of the entire human body. The hammer, anvil, and stirrup. And the mnemonic that I use to remember these three bones is that the ear has the three smallest bones, HAS, hammer, anvil, stirrup. Now there are other technical words for these bones, and you will see that in a video in just a few moments. Leading from the hammer, anvil, and stirrup, these tiny little bones, it is then connected into the inner ear. The inner ear is where you see the cochlea and the basilar membrane. This is where your sensory receptors actually are. The auditory nerve comes off the back of the cochlea and then travels to the brain. So again, you're seeing the pattern of the message being sent from the sensory receptor in the cochlea to the auditory nerve, that specialized nerve where it's going to travel to the brain. It's going to get sent to the thalamus that's going to determine where it is supposed to go, and it will be processed in the appropriate part of the cortex that is specialized to that sensory organ. All right, so let's talk about the cochlea. The cochlea is a coiled, bony, fluid-filled tube in the inner ear that transduces sound. This is where transduction happens. It transduces the sound vibrations to auditory signals. This is where it turns from a mechanical wave into something that our body can process.
Have you ever wondered how sounds make their way from the source all the way to your brain? Take a trumpet, for instance. When it's played, it makes sound waves in the air. The outer ear catches the waves, which then travel through a narrow passageway called the ear canal. The sound waves reach the eardrum, which is a membrane roughly half the size of a dime. They make the eardrum vibrate, which in turn vibrates three tiny bones called the malleus, incus, and stapes. These bones amplify or increase the sound vibrations and send them to the cochlea. The cochlea is shaped like a snail and is the size of a garden pea. It is filled with fluid, and the sound vibrations make this fluid ripple, which creates waves. Hair-like structures called stereocilia sit on top of hair cells and are grouped together as hair cell bundles inside the cochlea. The hair cells inside the cochlea ride these waves, and the hair bundles are moved. The hair bundle on top of the hair cell turns these movements into electrical signals. As the hair bundles are moved, ions rush into the top of the hair cells, causing the release of chemicals at the bottom of the hair cells. The chemicals bind to the auditory nerve cells and create an electrical signal, which travels along the auditory nerve to the brain. Different hair cells respond to different frequencies of sound. The hair cells at the base of the cochlea detect higher-pitched sounds, such as a piccolo or flute. The hair cells toward the top of the spiral detect progressively lower-pitched sounds, such as a trumpet or trombone. At the very top or apex of the spiral, the hair cells detect the lowest-pitched sounds, such as a tuba. The auditory nerve carries the electrical signal to the brain, which interprets the messages as sounds that we recognize and understand.
Okay, so let's talk about theories of hearing or audition. The frequency theory states that the rate of nerve impulses traveling up the auditory nerve matches the frequency of a tone, thus enabling us to sense its pitch. So we're able to sense the pitch based on the fact that our nerve impulse is the same as the frequency of a tone. Another theory is place theory. This suggests that sound frequencies stimulate the basilar membrane at specific places, resulting in perceived pitch. So because of where the basilar membrane is stimulated, that is what's going to enable us to be able to perceive the pitch. And this is what we just saw in the video. Localization of sound, because we typically have two ears, sound is going to reach one ear just slightly faster than the other one, and this is going to be able to help us localize the sound. This is something that you could actually test out with a partner. If you had someone who was willing to help you out, you could close your eyes and have them talk and walk around the room, and you could guess and see where they were. And chances are, as long as you have normal hearing, you should be able to figure out where they are just based on how your brain is able to translate the information coming in from each ear. Okay, hearing loss. Just like as you drive a new car off the lot, it depreciates, so does your hearing. As it is being used, your hearing is going to decrease. The ability to hear is going to decrease with use. The first concept involved in this is noise-induced hearing loss. This is the progressive inability to detect higher frequency sounds due to just typical damage, just everyday use to the hair cells accrued over time. Generally, any sound loud enough to produce tinnitus, that's ringing of the ears, is going to cause some damage. This is usually around 85 decibels. So think back to all of the pep rallies, all of the concerts, all of the times that you've been listening to music really loud, if you're in the band. All of those times that you had ringing in your ears after that event, you've had some hearing loss. That is why I always wear earplugs to our pep rallies. It's not that I don't want to hear, I can hear, it's just muffled and it's going to have less of a chance of damaging my ears. High intensity or loud sounds can actually tear off the hair cells of the inner ear. So over time, you can see the damage kind of accumulate. Okay, continuing with hearing loss, there are two types of deafness. Conductive deafness is hearing loss caused by damage to the mechanical system that conducts sound waves to the cochlea. So anything that's going to stop the sound waves, that process of going through the eardrum, those tiny little bones, anything that is going to stop the message from being sent to the cochlea is conductive hearing loss or conductive deafness. Sometimes it can be corrected with surgery or hearing aids. So if you see someone with a hearing aid, it is typically a conductive hearing loss. Sensorineural deafness is hearing loss caused by damage to the cochlea's receptor cells or to the auditory nerve, which is also called nerve deafness. This is a permanent condition. Now, certain types of sensorineural deafness or hearing loss can be assisted with a cochlear implant. A cochlear implant is a small, very complex electrical device that is surgically implanted into your body. It can help provide a sense of sound to a person who's profoundly deaf or severely hard of hearing. It does not restore normal hearing. Rather, it can give a deaf person useful representations of sounds and can help the person learn how to understand speech. So it doesn't make them hear. It's more that like it gives the person an ability to understand speech in a different way. And here we're going to see a video of an 8-month-old baby hearing for the first time because of a cochlear implant.
Here we go, it's coming back on, and he's back on again. See how he turns?
Turn. Hi, Jonathan.
Stop the sucking.
Hi.
Good.
Could you
real good.
hear that? Hi, sweetie. Could you hear that? Hi. Hi.
You got that, Dad, right?
Hi, Jonathan.
And that's it for this video. In our next video, we're going to be talking about the other senses. I can't wait to see you then. Bye for now.